so we're going to look at some of the consequences of the gradient vector today. This is how we compute it. Okay. What's a little bit confusing is the gradient vector also gives us a way of computing the directional derivative. So if I wanted to compute the directional derivative at a point, the way we're going to do that is we're going to evaluate the gradient at that point and dot it with our directional derivative, or with our directional vector that we're looking for the directional derivative in. Okay. So I think now that we've got these two new actors, it's really easy to start confusing things. This is a vector, and this is a rate of change. Okay, so what I'd like to do is, just as a warm-up, let's go ahead and compute the gradient for this particular function at this given point. So the gradient at the order pair 1, 3/2 is going to be what? Well, it's going to be 2, -3. Why is that? Because if you were to compute the partial derivative of this with respect to x, we get 2x. And so if we were to evaluate that at the point that we want to evaluate it at, 1, 3/2, that would just be 2 times 1, or 2. And likewise, if we were to do the same thing and take the partial derivative with respect to y, we would get minus 2y. And if we evaluate that at the ordered pair 1, 3/2, that would give us that minus 3 component. Okay. Everyone clear how we computed this directional derivative? Okay. Or sorry, not this directional derivative, this gradient vector. So we found the gradient at a particular point, right? And I already said this, we said this at the end of the class yesterday. What is this? What can we think of this vector as? We can think of this vector as pointing in the direction of the steepest ascent. So on our surface, the gradient in 2D will point in the direction where if we were to move that way, but moving along our surface, we would be climbing the steepest. Okay. So let's go ahead now and compute the directional derivative. So what we're going to do is we're going to look into the direction here. So here we have, in our domain set, we've got the ordered pair 1, 1.5. So that would be right about here. So that's 1, that's 1.5. There's 1. So that's the ordered pair right there, 1, 3/2. And so what we're going to do is we're going to look in the direction of this vector here, which is minus square root of 2 over 2 minus square root of 2 over 2. So we're going to be looking in that direction there. And we're going to ask the question, if we were to step in that direction, what would our rate of change be along that surface? What would our change in elevation be along that surface? Our instantaneous rate of change as we move in that direction. So we're computing that directional derivative. And let's go ahead and do so. This is going to be the gradient. So let's see. Directional derivative for this unit vector here, minus square root of 2 over 2, minus square root of 2 over 2, for our function f at the point 1, 3/2. That's going to be the gradient of f evaluated at 1, 3/2, dotted with the direction vector that we want to head in. Okay. So if we go to compute this, we're going to take our answer from before where we found that the gradient was the vector 2, -3. That was from part A there, where we said the gradient was 2, -3. And we're going to dot that with our direction vector. And when we clean this up, well, let's see, this gives us minus square root of 2 plus 3 radical 2 over 2. And if we add that together, we get the square root of 2 over 2. Double check the sign on that. Did I get that sign right? Yes. And a decimal approximation of that, if you plug it into a calculator, is about 0.71. Okay. So now we've done this work by hand, I'd like to again revisit this picture that we were looking at last time, where here's that surface that we had. Come on. I'm sorry, folks. I test everything out before class, and it works before class, and then we try it here. Anyway, I apologize for this. Okay, here's this function. Come on. That's the x squared minus y squared. And I'm going to plug in the ordered pair 1, 1 1/2, or 1, 3 halves. Okay. Notice the first thing that it calculates for us, as you can see, right here, it's computed the directional derivative. Or excuse me, it's computed the gradient at that point. And that was our first step, was to compute that gradient. Okay? So in light of what we said last time, we can see that that gradient is pointing in the steepest direction you can move. So from the point P, the steepest direction we can move is to start heading in this way. Okay? Then let's have it compute the directional derivative for us. So I'm going to turn on the directional derivative. You can see here that it's got this black vector here. That's the direction. Notice this black vector has a magnitude of 1. That's our u vector, or a u vector. It's not the one we were asked to use. And so what I'd like to do is I'd like to slide this till we're pointing in the same direction as we were before. And there's that direction, minus the square root of 2 over 2, minus the square root of 2 over 2. And what we can see here is, sure enough, the calculator, I mean, I guess we could believe the calculator, computed the directional derivative for us. But also, if I were to look up above here, what we're seeing is that if I were to head in the direction of this black vector here, does everyone see this? That's the same black vector that we have right here. If I were to head in that direction, my instantaneous rate of change is the slope of this line right here. And the slope of that line, we can see it's, I mean, you can at least see from the image, it's a positive slope. If you want to know exactly what the slope of that line is, it's what we computed when we computed the directional derivative. Okay. So the big result that we had is that, you can see that as I scroll through these different, each one of these, for this given angle of theta, and that angle of theta is not the angle between our black vector and the directional derivative, but it's just a given angle from the x-axis. But notice that each one of these, for each theta, I've got a different directional derivative, and you can see up here we've got the value of the directional derivative being computed. So for example, here we can see that if I were to step from my point right here, this is still at point 1, 1 1/2. If I were to step step in this direction here, in this case in the direction of negative 1, 0, so that's going backwards in the x direction, that my rate of change would be negative. And we can see that. I can't see the tangent line on there. It's kind of hard to see because it's so coincident with that parabola. But you can see that, yeah, as I step in that direction, my y values will be falling. But what we're interested in is where that directional derivative is the greatest. And that directional derivative we see is the greatest when we're moving in the same direction as the gradient. So the thing you need to keep in mind is that the gradient automatically calculates the direction of steepest ascent. So if you were to move away from this point, the steepest path you could take is in the direction of the gradient. So I can do that so I'll go ahead and slide this. I can move this point P around, and you can see that, depending on where I am, the gradient changes. But no matter where I am, if I go to compute my directional derivative, it takes on different values, but it's always greatest when I'm pointing in the direction of the same direction as the gradient. Where that steepest ascent is, depends on where on the curve I am. Okay. And by the way, I should just say that if I were to put myself right on this saddle point right here, everything breaks down. Because if you compute the gradient at a saddle point, you'd find that the gradient is the zero vector. Okay. Just to go ahead and tell you where we're going with this, we pretty soon want to do some Calculus 1 problems where we find maximums and minimums on a surface. And noticing where the gradient is zero is kind of a hint as to where we're going to be going with that. So, for instance, to find this saddle point, we could search for places where the gradient is zero. In this case, that saddle point is neither a maximum nor a minimum, but that fits with our original first, or kind of like our second derivative test, first and second derivative tests from Calc 1. Yeah.
So, will we ever need to find the unit vector in which we need to dot with our gradient to find the directional derivative? Like, are we ever going to have like an elliptical helix and you're like, at this point on the helix, find, the unit vector pointing in that direction, but also what is the, rate of change on this surface at this point on the helix? I don't know if that's making sense.
Well, the question of what's the rate of change at this point on the helix doesn't make sense because you can only answer that by specifying a direction.
Okay.
We will ask questions like, we could say, in which direction should you head so that you increase the fastest or that you decrease the fastest? Or if you head in this direction, what will be your rate of change, your instantaneous rate of change?
Okay. So we'll always basically be given the unit vector.
Well, not necessarily as a unit vector. You saw the first couple examples I gave you. I just said if you head in this direction and you had to convert that directional vector into a unit vector.
Okay.
But also, so yeah, that's a great question. So I think what you're asking is, will you ever have to, like if I say, find the direction you need to head in so that your rate of change is 3. Mm-hmm. And that question in general is too difficult to ask.
Okay.
I could say which direction should you head in so that your rate of change is 0. That's a fair question, and we'll look at that. That's one of your that's kind of one of your homework questions. And we will say which direction should you head in so that it's maximal, because that's heading in the direction of the gradient. Mm-hmm. But I think in general it would be pretty hard to because there's lots of direction. I think it would be kind of a hard problem to answer. Which direction should you head in so that the directional derivative comes out to be a particular number? Yeah.
Okay. So I guess a more simple way of what I'm asking is, you're never gonna ask us to find the direction of a path on a point and then take that direction of the path to...
No, I think so. That's similar to one of the ones in your exam review.
Okay, because then I'm confused on...
Okay, let's, so Phoebe, I think
sorry.
I'm going to encourage us, rather than doing hypothetical, like, will we have this question, let's kind of keep working through the examples, and that might kind of help us see a little bit more. I hate to say it, but some questions in Calc 3 are exceptionally hard to do, and some questions that may look exceptionally hard are quite straightforward if you notice a little trick. And so I can't really answer...
I just need to know if there's some trick, because these are questions where I'm I don't think I could answer that. I don't know how to go about answering
yeah, so let me just say, without having the question in front of me, I can't really answer how we would answer it.
Right.
Yeah.
I understand.
Yeah.
Sorry.
Okay, that's all right. Okay, so we answered in D here, we said, okay, it appears that you have the largest directional derivative in the direction of the gradient. And if there's one thing that you need to take home from what is the gradient calculating, it is the gradient points in the direction of steepest descent. Okay. So last time, I'm not going to repeat this, last time for number 22, we did a quick derivation as to why the gradient points in the direction of steepest increase. And that has to do with the fact that if you look at the cosine of the angle between them, that cosine expression is maximized when the theta is 0. So you can review that. You should have the notes for 22 there. Okay. So here again, I'm just summarizing those results here that says that f has a maximum rate of increase in the direction of the gradient vector. And what is that maximum rate of change? It's simply the magnitude of the gradient vector. Okay. Folks, be careful here. I did have a typo, so I had to change that to a minus sign here, and this to a minus sign here. So if you want to talk about going in the steep, so let's just make sure this makes sense. If you want to talk about the maximum rate of decrease, you're going to go in the opposite direction of the gradient vector. And if you want to know what that maximum decrease rate of change would be, it's simply the opposite of the magnitude of the gradient. Okay. Now, this next result we'll talk about some more. And so, kind of towards Phoebe's question, I will ask you, in which direction should you head so that your directional derivative is 0? Because the answer to that is simply to head in a direction that's orthogonal to the gradient. Okay. So that's what we saw in this demonstration here. Let me move this point somewhere else. Right up here you can see the value of the directional derivative. And if I adjust my angle so I'm moving along this level curve here, so the level curve is shown in red. And I can't fine-tune this perfectly, but you see that my directional derivative gets very close to 0. And that's because I'm heading in the direction of a level curve, and when you're on a level curve, what does that mean? That means your elevation isn't changing. So if I say, if I step in the direction of this level curve, how are my z values changing? Well, the answer is they're not. And that's why this directional derivative is 0 here, or as close to 0 as I can make it with this demonstration. Okay. So the next thing is that brings us to the idea of the path of steepest descent, which is a really interesting question, and you may not think so. Maybe, I guess if you were climbing a mountain, you want to say, well, given that if my legs could do whatever I wanted to do, which way should I go to get up this mountain the fastest? The answer is to go in the path of steepest descent. That question seems a little bit fictitious because you all know that you can't just climb up a mountain the fastest way. You have to take a shallower path often. But reverse the question. What's the path of steepest descent? And so, for example, if you had water falling on top of a mountaintop, that water is going to fall off the mountaintop, falling along the direction of steepest descent, which is simply the opposite path of the path of steepest ascent. So it's a really interesting question. And so I want to show you that real quick with this demonstration here. Okay. So here we can see this is that curve that whenever you pull up CalcPlot 3D that it picks first. And what I've done here is I've given the curve of steepest ascent. Let me just show that to you. So let's see here. Is this the wrong one? Yes, it's the wrong one. This is that curve of steepest ascent here. Come on. And you can see my point moving along here. And this point is moving in such a way that it's climbing up this mountain the fastest. Now that might be a little bit surprising to you, because you might have said, well, why didn't I just take this path right here? But the answer is that at the point where this curve started, if I were to start heading up the mountain, what I'd have to do is first actually go downhill and then up. As opposed to, you can see the darker red here, which is pointing in the direction of the steeper increase. And so that's the way we head as we do this. So we'll do one question here where we actually find the curve of steepest descent. Okay. But I want to give you a kind of another sense of how we could look at that. So I'm going to move this. What you can see here is I've got this other point shown in blue here. You see this point here that I'm now moving around? I'm going to try to start it right on top of that other point. Actually, I can just tell it to go to, let's see here, where was our point? Oh, that's fine. That's close enough. Okay. So you can see that this blue point now is oriented on our surface about where this curve starts. And what I've told the CalcPlot3D to do is to point in the direction, or to show me the gradient vector here. So you can see the gradient vector pointing this way, and that's because that's the path of steepest increase. So what I want you to think about is if I were to step along that path of steepest increase, so let's step that way. So what I'm going to do is I'm going to click the mouse midway in the middle of that vector. So I'm heading along that path of steepest increase. You see that? That brings me to a new point. And at that new point, CalcPlot3D calculates the gradient vector. It's a new gradient vector. It's pointing in a little bit different direction. What I'm now going to do is adjust my movement and move in that direction of the new gradient vector. So again, I'm going to step kind of halfway through that vector. And you can see that this continues. Now, notice that I'm leveling off, so my gradient vector, the magnitude of it, is becoming less and less. You'll have to bear with me because it's not a perfect demonstration. Come on. Starting over. All right, there. Because that gradient goes to, it's very close to 0, but it actually technically isn't quite 0. So I'm going to keep heading along that. My vector is going to get a little bit bigger there. I'm going to keep stepping in the direction of that vector. And what do we notice, folks? It's a really important idea. As I keep stepping in the direction of that gradient vector, I'm arriving eventually at what? One of the maximums of this surface. And that's because the gradient is always, at each new point, the gradient is adjusting to point in the direction of steepest ascent. And so that path will take me up to the maximum of a function. Okay. All right, let's go on to the next page here, page 7. So now I'm summarizing what we just saw here, in kind of two different ways. The first way is just to say that at a level curve, if I were to draw a tangent line at the level curve, along the level curve, then my gradient is pointing orthogonal to that. The direction of steepest ascent is always going to be orthogonal to my level curves. What that means is that if I've got a parameterization of a level curve, then the derivative of that parameterization is always orthogonal to the gradient. And so here you can see an example of a path of steepest ascent, where you move in such a way that your curve is, this new curve, this curve of steepest ascent, is always orthogonal to your gradient lines, or excuse me, to your contour lines. Okay. We're about to do an example from the textbook, and the textbook didn't really mention how they got there. They just went ahead and did it. So I want to say that I think these are two useful bits of information, and that is if you want to think about projecting a level curve down into the xy plane. So we've got some surface, and on that surface, maybe I've got this level curve here where all the z values are constant on that surface. So if I want to think about projecting that back down onto the xy plane, that would be this curve down here. Okay. So this curve down here is going to satisfy what's called a differential equation. dy dx is equal to minus partial f's of x, partial f's of y. Okay. If you're interested in that, I'll just say come see me in office hours and I can show you how we got that. I was hoping to make a video for it that I could point to you guys to, but I haven't had time to do that. Okay. So if you were to solve this differential equation, you would have the projection of the level curve in the xy plane. What's beneficial about that is that you can actually come up with a parameterization for the level curve by then taking that equation in the xy plane and bumping it back up to our surface. Okay. Likewise, this should look a little bit familiar here, folks. If you want the differential equation that describes the path of steepest ascent, you're going to solve this differential equation. And what I want to point out is, how are these two differential equations different? In an algebra class, we would have said that those two expressions are negative reciprocals of one another. Do you see that? So if I were to take the reciprocal of my differential equation that describes a contour line, and then change the sign on it, take the negative reciprocal, I'd have this expression here. And that's related to the fact that the gradient is always orthogonal 90 degrees, right? The negative reciprocal of, in terms of slope, the negative reciprocal of a level curve. Okay? So let's go ahead and try this real quick. So to Phoebe's question earlier that I was having a hard time answering because it really just depends on the question, here's an example where I say, in what direction should you go so that there's no change in your functional values, your z values? Okay? So of course, the answer is, in a not very helpful way, is to move along the curve f of xy is stuck equal to 61. If you keep moving along that curve, then your z values aren't going to change. But that doesn't really tell us what direction we're supposed to head in. Okay? So what's our strategy here? We know that the gradient, so let me just say that that's not helpful. Even though it's true, it's not helpful for finding that direction. But what do we know about, what do we know about? We know how to compute the gradient, and we know that the gradient is orthogonal to the direction we should head in if we want to not change our height. Okay? So we want to go in a direction, so here's a better answer. Go in a direction orthogonal to the gradient. Going back to that picture here, this is the direction we should be heading if we don't want our z values to change. That's following along that level curve. But to actually know what that direction is, we're going to first compute the gradient and then give a unit vector that's orthogonal to it. And there'll be two of them. There are two unit vectors orthogonal to the gradient vector. So this little unit vector right here and this little unit vector right there. So those are the directions we should head in. So to answer the question, let's first compute the gradient of f at the ordered pair 3, 4. Well, to do that, we need to first compute partial f, partial x. I'm going to use the other notation. Let's compute partial f's of x at the ordered pair 3, 4. And let's compute partial f's of y at the ordered pair 3, 4. Okay. Well, partial f's of x is just 2x, and partial f's of y is just 6y. These are kind of easy examples. The calculations aren't hard, but so here we get 2 times 3 is 6, and here we get 6 times 4 is 24. So that tells us that the gradient is the vector 6, 24. Okay. Now careful here, is that our answer? No, this is an answer that's orthogonal to our answer. Okay. So let's let the first x coordinate. Let's say so we want, let's say it like this. We want do I have an A and a B here? No. We want A comma B so that 624 dotted with AB is the zero vector, or sorry, not the zero vector, is the number 0, so they're orthogonal. So let's pick A equal to 1. And if A is equal to 1, then we'd have 6 times 1 plus 24B needs to be equal to 0. We probably should have picked for B instead. Anyway, we get that B is equal to minus 1/4. So one direction we could head is to head in the direction of 1 comma minus 1/4. Another that we could head is in the direction of minus 1 positive 1/4, heading in the opposite direction. So one of those corresponds, in our picture here, one of those corresponds to this vector, one of them corresponds to this vector. Now, a better way to do this is to give it as a unit vector. I'm not going to worry about doing that right now. Okay. Do you see that if we gave it as a unit vector, then we'd all agree, we would all, no matter what number you'd picked for A, what number you'd picked for B, if you then converted it to a unit vector, we'd all give the same answer. Okay. So I'll just add to that, convert these to unit vectors, so we all agree on the answer. You wouldn't, but it's not really a big deal. Any questions about that? So that's sort of like Phoebe's question here, right? What direction should we head in order to ensure that our directional derivative comes out to be 0? Okay. Let's move on to the next page. The next question says to project the curve z equals 61, this is for the same function, into the xy plane. Okay. So we can sort of do that because this is a, oops, I can't scroll up. Hang on just a second. This is the graph of a paraboloid. So what we're saying here is here's this paraboloid, and it's elliptical paraboloid. We'll actually look at its picture here in a second. But this might be the level curve here where z is equal to 61. Okay. Now, what I'm about to do, you could do another way, right? Like if you could remember a parameter, if you know that the shape is an ellipse, and if you remember how to do a parameterization of an ellipse, you could just go ahead and do so. Okay. But I want to show you a more general way that this will always work, even if your level curve is more like this one right here. So like if you were to project that down into the xy plane and then find that path of steepest ascent, or if you wanted to do a level curve on that, it might be quite a bit more difficult to parameterize. But to keep the numbers easy for us, let's do it for this paraboloid. So what we're doing here is I'm saying project this down into the xy plane, that's going to be some sort of ellipse, and then find an equation for it. So let's go ahead and do so. I said, so that goes back to that formula right here, or this expression right here that says, if you want to find the equation of that projection of a level curve, you're going to solve this differential equation right here. By the way, that should look familiar. That looks like your implicit differentiation formula. And that's why we had to derive those at the beginning of last class. So we know that we need to satisfy the differential equation dy dx is equal to minus f sub x over f sub y. Now, I don't know whether everyone learned how to solve differential equations in their Calc 2 course. So we've started, I know here at Front Range, we started teaching how to solve very simple, what are called separable differential equations in our Calc 2 courses. So maybe you've seen this before. If you haven't, it's not very difficult. You do something called separation of variables. And so I'll show you how to do that here, even if you haven't seen it before. I think you'll be able to keep up. So first of all, let's compute, well, I think we did that already, right? Did we compute f sub x and f sub y? I think we had to right here. So let me grab those. So we need to satisfy, dy dx needs to satisfy the differential equation, negative 2x over 6y, which is, let's go ahead and simplify that first. That's the differential equation, dy dx is equal to negative x over 3y. Okay. So, folks, if you haven't seen this technique before, it's actually not very surprising. We're doing something called separation of variables here. What I'm going to do is I'm going to multiply the 3y over to the other side so that it's with the dy. And then I'm going to multiply the dx over to the other side so it's with the x. So I'm taking all the y variables and their respective and its differentials over to one side, and all the x variables and its differentials over to the other side. Okay. If you don't like that, if you don't like manipulating differentials that way, come see me and I'll give you a better explanation for it. But that's the net effect of what we do. We multiply it like this. What I'm then going to do is integrate both sides. So this is maybe new to you if you didn't see this in your Calc 2 class, but I don't think it's that surprising. You separate the variables, you have a dy and a dx on each side, and then you integrate both sides. So when we do that, I get 3/2 y squared is equal to minus 1/2 x squared. And then both of these would have a plus c, but I'm going to collect them together over on this side and just put my plus c here. Let's go ahead and finish solving for y squared there. So I multiply everything by 2. Now, I just said I wanted to multiply everything by 2. If you haven't seen this before, what I really have is 2c there, right? But c stands for an arbitrary number, right? A yet to be determined number, an arbitrary constant. And if I multiply that by 2, it's still an arbitrary number, doubled. So I'm just going to go ahead and leave it as a c, just so I don't have to give different c names through each step of this process. Continuing to solve for y, we get y squared is equal to minus 1/3 x squared. Again, what I have is c over 3, but I'm just going to write that as plus c, and we just all agree that that's not the same c as that one. Each one of those c's is different, but it doesn't really matter because we haven't had to specify what that c is yet. Okay. So put another way, then we get that y is equal to the square root of c minus 1/3 x squared. And I need a plus or minus on there when I solve for y. But then we go back to the actual point that we're talking about on this, let's see here, on this surface, which is the ordered pair 3, 4, 61. So on the surface here, up here we've got the ordered triplet. I just said pair, I meant triplet. We've got the ordered triplet 3, 4, 61. And so that gets projected down here to the ordered pair 3, 4. Okay. So I need to pick a c value so that my y value comes out to be 4 when I plug in an x value of 3. So first of all, we want to take which of these two answers. We want to pick y equals the positive square root of c minus 1/3 x squared. If I took the negative one, there would be no way I could solve that. for C. Okay. Then I'm going to go ahead and plug in the ordered pair. So 4 for y and 3 for x. And then I'm going to solve for that C value there. And maybe I should have done that earlier. I don't know. You could have solved it earlier in the equation for C. But what we're left with is 4 is equal to the square root of C. Let's see, that would be C minus 3. Squaring both sides, so you can see there's a little bit of kind of undoing what we did. We get that C would be equal to 19. So finally we can give our answer that describes this, at least a portion of this curve. And this only applies for y values greater than 0, so it's going to describe this part of the curve. But that's going to be the curve y is equal to the square root of 19 minus 1/3 x squared.
So here, would it be all right? Because like when we go here from integral 3y dy equals integral negative x dx, and then we have y squared and x squared on each side, could I just move the x squared and the y squared to the same side of the equation? Because then you have the equation of a circle.
That's, oh, an ellipse, but yes.
You have to isolate y.
No, you don't. This is what's called giving an explicit solution. So no, you didn't have to do that. But Dustin, what we will need to do is in the next step is I'm going to ask you to parameterize the curve actually. So this equation describes this curve, and your equation would as well.
Right.
But then we're going to say parameterize this curve up here. And to parameterize up that curve up there, we're going to have already solved for y. So maybe we did a little bit too much work in this first part, but that's going to make the second part a little faster. Yeah, great question.
So why couldn't we have just said that, like, why couldn't we just replace z with 61 and then gotten the equation 61 equals 4 plus x squared plus 3y squared? So, like, wouldn't that be a level curve?
Yeah, so that would work because our what we're going to run into is in more complicated functions, this is the method for doing it. And we're going to do this also for the path of steepest ascent or descent. And so this same technique applies. So I guess I would just say that we're kind of learning the technique, even though there may have been an easier way to do this problem. Yeah, great question.
Can you scroll up to A just briefly?
I can. Maybe.
Okay, that's good, thank you.
Yep. Okay, so now we're asked to give a parameterization of this paraboloid here. And so the way we can do the parameterization is to say that, so we'll pick x is equal to t, then y would be equal to the square root of 19 minus 1/3 t squared. And then we'd have that z would, and then we have to go back to the actual original function. So we've got z is equal to, I think it was 4, was it minus x squared? Yeah, I think minus x squared minus 3y squared. Was that our original function, folks? I'm just trying to save jumping back to the previous slide. Plus, those are plus. Okay. So we get that z then would be equal to 4 plus t squared plus, and I'm just going to not worry about simplifying it, 19 minus 1/3 t squared quantity squared. And so then that gives us a parameterization of this, of not the curve down in xy space anymore, but of the level curve up there. And the parameterization that we did will only hold, let's see here, well, it only holds for where this is defined. So let's see here.
Can you go back for a sec? How do you know that x equals t?
That's the choice. Remember, there's many ways to parameterize something, Xavier. sometimes we choose things that make our lives a lot easier for calculations. Like we choose to parameterize x as the cosine of t, or r cosine t. We choose different parameterizations. So we may choose x to be like a cosine t and y to be a sine t if we know that we've got a circular region. But you can always, once you know what y is in terms of x, you could always let x be the simplest variable and then just sort of ladder your way through that. So I say...
Then why didn't you pick x equals 0?
Well, that's not a variable. It does have to be a variable. I mean, that would give you a point. If you pick that, that would give you 1 point on the curve, but that wouldn't give you a parameterization.
Okay.
Yeah.
Professor, I was looking at the original of the equation. That should be 3 times the square root of 19 minus 1 over 3t squared.
Thank you. Everyone hear what Christopher said? So yeah, so that should be a 3 there. I dropped it when I was converting. Thank you. Okay, so rather than keep going with this example, what I'd like to do is just look really quickly at this next example. We're not going to work all the way through it, but I'm going to set it up for you. So in this case, we've got the same ball, or we've got a ball being placed at that same point on that paraboloid. And we want to ask, what is the curve of steepest descent? And so the way we're going to think about this is we're going to take that paraboloid, and this curve of steepest descent would be some curve that's always doing what, folks? It's always following the opposite of the gradient vector. Okay? So at any point, my gradient would be pointing, let me zoom in on that. So for example, right here, at this point, my gradient would be pointing this way. And so the ball, as far as steepest descent, is heading in the opposite direction of the gradient. And if we were to project this curve down into the xy plane, this curve would look something like this as the ball moves along the path of steepest descent. The reason why it doesn't fall in a linear fashion towards the origin is because this isn't a circular paraboloid, it's an elliptical paraboloid. Okay. By the way, we're not going to consider that this thing has, we're not going to take into account the momentum of the ball. Okay. I don't know if that would affect things. Okay. So I'm just saying, if you had a drop of water and it fell slowly down, which way is it going to go? It's going to follow the path of steepest descent. Okay. So again, if this were a circular paraboloid, it would just fall straight towards the origin as you project that down into the xy plane. Because it's elliptical shaped, it's not going to do that. So I think all I'm going to do here to finish this up, because I want to get us to the answering your questions from the review, is to say that this path of steepest descent is going to obey the differential equation dy dx. And here what I'm going to do is I'm going to worry about changing the sign on the problem afterwards. Let's find the path of steepest ascent. Okay. So the path of steepest ascent would be, double check me here, this should be f of y over f's of x. What do I mean by double check me? That's this idea here. Nope, from the previous page 6. Oh, my pages got out of order somehow. From page 7. That's this idea right here, that the path of steepest ascent, or you just change direction for steepest descent when you're done with it by changing the direction of t, putting it in minus t, obeys this differential equation here. Okay. I don't think it's clear where that real quick, Xavier, before your question, I don't think it's clear where that differential equation comes from if you just look at it on its own. But if you compare it with this differential equation that we just did for the path of the level curve, then we see that we're setting up a differential equation to force the dy dx, that's the change in y with respect to x, that's the slope of the tangent line. We're forcing the slope of the tangent line to always be the negative reciprocal of the slope of the tangent line that keeps us along the level curve. And so that's going to force us into the direction of steepest ascent. Yeah, Xavier.
If it were to ask me what's the path to steepest descent, I would just take gradient.
That would give you, so if you took the gradient at a point, Xavier, that will tell you which direction you should initially head in. The hard part about that is, as we saw right here, let me move this point back to that initial point here. That's about the best I can do there. You could see that the gradient, that red vector, is pointing in the path of steepest descent, right? But that doesn't mean I keep going in that direction all the time. Right? So at each new point, we have to reevaluate that. So you can see that as I move along that path, well, you can see that direction of steepest ascent changes as we move along that path. Okay. Let me put my tangent vector on there. For this blue curve. If I tell it to put on the velocity vector for this blue curve, wrong one. If I put on this velocity vector for this blue curve, that vector is always, that's the biggest that vector can ever be. Okay. And any other direction would result in a smaller vector. That's why I'm going up the path of steepest descent there. That's one way to kind of look at that. So what you're saying is that, yeah, if I said what direction should you initially head in to go in the path of steepest descent, you would just compute the gradient. But if you want to give the curve that continues along that path, you have to solve this differential equation here.
Okay, thank you.
Yeah, it's a good question. Where were we? We're on page 9. Okay. So what we do in this case is we'd solve the differential equation dy dx is equal to, and then I think we had 6y all over 2x, or that reduces down to the differential equation dy dx is equal to 3y over x.
So I have another question. Why did you do fy over fx instead of negative fx over fy?
Yeah. So in the last example, we were trying to stay along the level curve. In this case, we always want to be orthogonal to those level curves. And so I've taken the negative reciprocal of the previous problem. It's a differential equation.
Oh, okay.
So in the last problem, so just for any old case here, you know, here we've got the level curves in the xy plane. In the last problem, we were trying to find an equation that kept me on a level curve. And so that would be to solve dy dx was equal to minus f of x over f of y. But now I want to always move perpendicular to those level curves. So I'm going to solve the differential equation dy dx is equal to f of y over f of x, where that's the negative reciprocal. Okay. So folks, I'm going to leave this here because I think that I've done my duty in showing you how to compute these curves of steepest ascent. And I'm just going to say I'm not going to ask you to solve these differential equations. But this is our strategy for finding paths of steepest ascent and descent. And again, that's really useful because what we have then is we have a way of finding a path starting at any point solve the differential equation, and it will take you up to a maximum of your curve. Or if you think about it, if you're doing something with like modeling water flow, if you want to say water falling in this region here, where does it end up at? You're going to follow the path of steepest descent to see where it goes. Okay. If you'd like more on that, let me know. I think that's all I want to say about this section. Let's see if I've got anything more here. Yeah. I do think that it's very helpful to keep in mind what I've written on this page here, the last page. And that is, we've got all these new actors here. It's very easy to get confused with what you're doing. Okay? So I'll let you run through these, but I just reiterate that, f sub xy is a function from R2 to R. So then the graph lives in the space of R3. The gradient is a vector-valued function that takes vectors in the domain space to other vectors in the domain space, R2 to R2. So for example, if you compute the gradient at a point, that's a vector in R2. When you compute the directional derivative, you're computing a number that tells you the instantaneous rate of change if you move along a surface in that direction. Okay. So I think this may be a particularly helpful summary of what we just learned. Okay. Let me stop the recording.